Okay, thank you very much. I'm very happy to be here, and it's great to have so many of you in such a lovely room today. So I'm going to be talking about some work that we've been doing, thinking about planetary systems outside the solar system, thinking about what they're made from, and how we can use that to understand their potential habitability. So we all live on this beautiful planet Earth, and so when we look to planets outside the solar system, Earth kind of gives us this guide as to what we might be thinking about in terms of habitability. This life may not or may not be like life on Earth or on another planet, but at least the one place where we do know that is habitable is our planet. This kind of image is taken from the moon, and already then we can see very little about our own planet. Right? You might be able to kind of just work out that there's a lot of clouds and maybe kind of faintly see that there's some kind of land underneath that. But when we go to kind of exoplanets, we're really dealing with a totally other kind of scale. Our information is very, very limited, and we have to use other kind of insights to try and deduce as much as we can about those planets. But we're lucky, we're on the cusp, really, of finding planets that might be like Earth around other stars. We kind of started this journey over 20 years ago now with the discovery of the first exoplanets. And we're now kind of moving to the point of being able to find things that may be rocky planets, that may be kind of Earth-sized, Earth-mass planets, although a lot of these tend to orbit the kind of low-mass stars rather than kind of stars like our sun. And the future is bright. Hopefully, within the kind of next 10 years, we'll be finding lots more of these kind of planets. But are they habitable? Well, one of the simplest things we can say about habitability is to think about whether or not we can get liquid water on the surface of those planets. So we can define something called the habitable zone, and we can look at how much starlight those planets receive, and whether or not we think there should be liquid water sat on the surface of those planets. And we now have a kind of growing collection of planets that sit in this kind of perfect zone where there is the right amount of stellar radiation such that you should have liquid water on the surface. Those planets tend to be around these low-mass stars, M-dwarfs, rather than around kind of sun-like stars, as you can see from this plot. And this figure is actually getting a little bit out of date now. There's quite a few more planets in there. But is having a planet that's the right temperature enough to make a planet habitable? What else can we learn about? Well, those who know me better know that I really care about what planets are made from, and how we can use insights regarding the kind of interior composition to kind of learn about what those planets might be like. Do they have cores? Do they have mantles? What kind of minerals do they have in those mantles? And what kind of rocks do they have on the surface? And what does that lead to in terms of kind of surface topography and so forth? But finding out what a planet's made from, so planet's interior structure can be crucial, and it's really, really hard to find out about. So if we kind of look at these kind of cartoons, we can see that we could have a lot of different things going on, right? For our own planet, we know we have this iron core that's molten and has been important for kind of generating magnetic fields for our planet. But do we have that for other exoplanets? And what do those potentially look like? There's a lot of things we'd like to learn about planetary interiors as well. But it's not just the interior that composition matters for. It also matters for the surface of the planet, right? So if we look at kind of Earth from space, we try and deduce whether or not it's habitable. We actually have a very limited view of what the surface is like. We think maybe we need to kind of have solid land in amongst kind of the liquid oceans in order for us to kind of have somewhere to reside upon. But if we look at the surface of the moon, that's a very similar kind of rocky body, but the surface is totally different. And how does that affect the habitability of that planet? Right? It's covered in craters from all of the kind of impact bombardments that we might have had. And composition also affects what's going on in the atmosphere. And atmospheres are absolutely crucial to habitability of a planet. So I don't know whether we can see this plot at all, but I'm trying to kind of show the hazy kind of tiny amount of gas around a planet that's potentially absolutely crucial to its habitability. And for exoplanets, what's really exciting is that we're starting to kind of characterize what's going on in the atmospheres of these planets and really to kind of learn about how they may have atmospheres that are very, very different from our own, if they have atmospheres at all, and how those evolve and are sustained. Okay, so back to the kind of exoplanet revolution. I love putting up this diagram because I think it really shows us the diversity of exoplanets that we're finding around other stars. None of them have really kind of shone to us as being just like Earth. Actually, we found things that we never expected to find. We found sub-Neptunes, we found super-Earths. This is an artist's impression, so we have no idea what the colors are like, what's really on the surface, but potentially planets may have the kind of diversity that we see here. And I'm sure you've seen this diagram before, but it's just to kind of highlight the wealth of information that we have now for exoplanets. So there's more than 6,000 planets detected. This is showing their kind of orbital periods and masses. And you can see that there are lots and lots of very massive planets, things like Jupiter, orbiting on short period orbits around nearby stars. We're starting to kind of get down to these low mass kind of rocky planets over here, but we really haven't found anything that resembles our solar system yet. Venus and Earth are really sat there on their own in this kind of diagram space. We do have rocky planets, but those rocky planets, as I said, are around low mass stars. So this is now a plot of kind of planet mass against planet radius. And you can see that these kind of contours show you things that would be rocky and would be kind of Earth-like. And we have quite a lot of data for planets now that really are truly in that rocky regime. But most of these, as I said, orbit those kind of low mass stars. And looking to the future, things are really, really bright. So Plato is going to launch either at the end of next year or very early in 2027. And Plato really is going to revolutionize our understanding of these rocky exoplanets. So not only will we better characterize the stars, but we'll be able to detect hundreds, if not thousands, more planets that really are truly rocky. And Plato has the aim of finding something around a sun-like star so that we can observe things for much, much longer to really find that thing that's on a year orbit rather than being on these close-in orbits. And then kind of looking further to the future, to the 2040s, when we kind of reach this era of kind of rocky planet atmospheric characterization with missions such as Habitable Worlds Observatory or the Large Interferometer for Exoplanetary Science that are really kind of going to be thinking about characterizing those rocky planets for us. Okay, so the talk today, I'm going to split into kind of two halves. I'm going to start the first half really talking about the planet's interior structure. And then the second half, I'm going to be talking about the planet's surface. And in both cases, I'm going to be thinking about how we can learn about exoplanet interiors and surfaces and use that to inform our understanding of their potential habitability. So probing the interior of an exoplanet is tough, right? If we're lucky, we have a minimum mass from a radial velocity measurement, so we can kind of weigh the planet. If we have a transit observation of the same planet, so it happens to pass in front of its host star, we can see how large that planet is relative to the star. And from this, we can get a density. That density estimate is really important for telling us whether that planet is rocky or gaseous. But actually, there's a large degeneracy in trying to understand what the interior of that planet might be. Exactly the same combination of mass and radius can give you a multitude of different structures. So here I've just illustrated how for the same mass radius, you could get a planet which was entirely uniform with no core. You can have a planet which has a mantle and a core, or indeed an ocean, a mantle and a larger core. And all of those make that kind of same radius mass diagram. So how can we learn about more detailed about the composition of exoplanets? Well, there's a few things that we can do. But if we imagine that we were kind of Earth scientists or cosmochemists thinking about things within the solar system, what we would want to do is to have a kind of sample of a rock, maybe kind of smash it to pieces and try and understand really truly what that rock was made from using some kind of mass spectrometer in the lab. For exoplanets, we can't do that with a whole planet. But the joy of astronomy is that although we can't get things in the laboratory, we can use space as our own laboratory. So we can look throughout the universe for a particular location where we can learn about these things. And so we can look and find somewhere where actually planets are smashed to pieces, and we can use that as a laboratory to study what planets are made from. And those of you who already know me will know that I'm talking here about white dwarf planetary systems. So white dwarfs are the faint remnants of stars like our sun. And this is an artist's impression of a kind of planetary body being torn to pieces by the very strong tidal forces around that white dwarf. And the planetary dust that ends up in the atmosphere of the white dwarf is a very, very useful way for us to see what planets are made from. because it shows up in the spectrum of that white dwarf. White dwarfs should have these beautiful, pristine hydrogen-helium spectrum. And we know that elements that are heavier than hydrogen and helium sink out of sight on a timescale that we can calculate theoretically. It goes from days for the hottest white dwarf to millions of years for the coolest white dwarfs. So when we find a kind of spectrum like this is flux against wavelength, and we see a kind of features from a whole load of different metals, we can use this to deduce what the planetary dust that was sprinkled on the top of that white dwarf was made from. So we can see lines from calcium, magnesium, sodium, chromium, titanium here, and nickel. All of those are telling us about the ratios of those elements to each other in the planetary dust that's in the atmosphere of these white dwarfs. And so this is incredibly powerful, and we can use this technique to study the composition of exoplanets. So how else can we learn about the composition of exoplanets? The thing to remember is that we can take spectra, we can take spectra of sometimes of the atmosphere of the exoplanet when we happen to kind of have things aligning in the right way to get a transmission spectrum. But all of those exoplanets have a host star. And doing spectroscopy of the host stars is a very powerful way of learning about the exoplanets. So those host star spectra can tell us about what those stellar systems are made from. And so they tell us the kind of elemental composition that's available for planet formation within those systems. We have to think carefully about how the link between that host star composition and the planets, because it's not the same as for the white dwarfs, where we're seeing the planetary dust. Here we're seeing the material that might be available for planet formation reflected in the star. And so we have to ask the question, well, what's the link between host star compositions and exoplanet compositions? But stellar spectra are much easier to do. So this is a spectrum of an F star. And again, you can see these beautiful strong lines from things like calcium and sodium that really tell you what that star's made from. Stars and planets form out of that same material. And so in principle, by knowing the material that the stars formed, we know what material is available for us to form planets in that system. And if we make some assumptions about how planet formation happens, we can use those stellar compositions to tell us about the exoplanets that formed around those stars. So this is some work by Haiyang Wang back in 2018, where he looked at the composition of the stars around these 5 exoplanets and used them to deduce some properties of what he thought the planets were that could form around those stars. So for example, up here on the right, you can see this little plot where he used the magnesium to iron ratio in the star to deduce what's the size of the core of a planet that likely formed in that system. And likewise here on the left, he's using the silicon, the iron and the magnesium to deduce what's the likely mineralogy of the material in the mantle for these different planets. And that mantle mineralogy can tell you about whether that mantle can store water, how viscous it is, and so forth. So these are really important constraints, but we have to ask the question, do stars and planets really share the same composition? And the best test case that we know is obviously the solar system, where we know the solar composition very, very well indeed. And actually we know planetary compositions from the solar system very well. And one of those planetary compositions that's very pristine is that from chondritic meteorites. And so this plot is showing us that the composition of the sun matches the composition of chondritic meteorites in a kind of one-to-one relationship for all the refractory elements. Clearly, the noble gases and some volatile gases like carbon, nitrogen, oxygen don't match. And those are the things that are influenced by planet formation and not necessarily incorporated in that one-to-one ratio into the planets when they're forming. Could we test this for rocky exoplanets? Could we show that we really have this match between host star composition and planet composition for an exoplanetary system? Well, ideally, we'd love to do that because then we can use our stars to really learn about our rocky exoplanet composition. But as we said, the interiors of rocky exoplanets are really hard to probe, so this is a very hard test to make. So instead, we look to binary systems. So binary systems are systems of stars that formed at the same time. And if we take kind of the early stages of planet formation and go back to these kind of big clouds of molecular gas, which are collapsing down to form both stars and planets, what we realize is that both stars and planets are forming out of the same material. That same starting material, the same elemental composition is going to be available for both the stars and the planets to form. In the universe, binary stars are incredibly common. And when we look at particularly wide binaries, so these things that are about 1,000 AU apart, what we find is that they are chemically homogeneous. So they form out of the same material, and they have the same elemental composition, clearly, to some degree. And there are occasional exceptions to this. But we can use that property that these wide binaries have the same composition to make this test of whether rocky exoplanets truly match their host star composition. And we did this by looking at white dwarf with a main sequence binary companion. And these systems, they're about a few thousand AU apart. And the assumption we're making is that both two stars form at the same time out of the same material, so they should have the same composition. One of them then evolves off the end of the main sequence. Its planets survive, but we now can't see them because they're in a very faint system around a white dwarf. You then get this kind of sprinkling of some planetary dust from that system onto the white dwarf. So when you look at the spectrum of the white dwarf, you're seeing the composition of some planetary dust from that system. And what we're doing is we're comparing that to the composition of this binary companion. And we're saying, do host star compositions match rocky exoplanet compositions through this comparison? And so back in 2021, we did this for the best system that we could find to study. And in this system is also really good because the white dwarf seems to have accreted something that's like a kind of comet. So it's contains both oxygen and carbon in the white dwarf spectrum, as well as a whole load of refractory elements. And what we found was that for all the refractory elements, there was a really good match between the planetary dust from the white dwarf and the binary companion. So calcium, magnesium, iron, silicon, they all matched between the two. There's a very tentative offset in the carbon, which isn't statistically significant, but could potentially be related to the fact that both carbon and nitrogen are volatiles and behave differently during planet formation. So more recently, we did the same experiment for another system. So these systems are really hard to find because there aren't very many white dwarfs that have lots of elements characterized in their atmospheres. And then not many stars have wide binary companions. But this system is a very interesting one because it shows a kind of different story. So here I'm plotting just the titanium calcium and silicon calcium abundances for the white dwarf. So there is a degree of uncertainty in what those abundances are for the white dwarf, and that's because they might have sunk out of sight at different rates. And we don't know whether accretion's ongoing or has finished for this white dwarf. And so that leads to the kind of blue, orange, and green points on this plot. And then we compared that to the companion to this star that's about 1,500 AU away. And we took spectra of that companion, and we deduced the composition. It turned out that there was already a composition in the literature from apogee, which is also shown on there as one of the black triangles. But the 2 points from our paper are the kind of 2 points in the middle here that sit with the other stars. And so what you see here is that potentially this binary has formed some planets, but those planets are depleted in things as a function of how volatile they are. So the silicon is depleted relative to the calcium and titanium during planet formation. And so calcium and titanium are much more refractory than silicon and magnesium. And so if you have high temperatures during planet formation, then and thermal processing, you can deplete those elements. And so what we think is going on here is that we see evidence for how planet formation can also alter the abundances that you see in a planet, so that you start from something in your host star, but that you can actually change the abundances that you see inside of your rocky exoplanet. Okay, so we're very excited about white dwarfs and binary systems as a way to test whether rocky exoplanet compositions match host star compositions, but are there any other ways that we can test this observationally? So we started thinking about where else we know about planetary compositions. And one of the places that we we can infer something about what planets are made from is actually in these near-infrared spectra of debris disks. So these are kind of things like our asteroid belt, except that they contain a lot more dust, and they're very warm, kind of in that inner region around stars. And what's really nice here is that the warm dust has this massive feature at kind of 8 to 10 microns from that silicon dust. So this kind of big bump that you're seeing here at the left at kind of 10 microns, that's because the dust is predominantly silicate, and it has this very big emission feature at that wavelength. What's interesting about this emission feature is that the exact peaks that you get from that feature depend on which minerals you have in that dusty material. So whether you're dominated by pyroxene or olivine can change the kind of peaky structure that you get from these kind of near-infrared spectra. And this is super because actually we're learning about the exact minerals that are forming that planetary dust. And if we think about it in terms of a bulk elemental composition, we're actually learning about how much magnesium there is to silicon in that planetary dust. And so our kind of working hypothesis would be that if you form in a system that has a particular Mg to Si ratio, you would form with a particular amount kind of composition mineralogically of your dust, and that you should be able to kind of see that in the near-infrared spectra. And so I'm going to encourage you all to go and talk to Claire, who I think is here somewhere, who's got a lovely poster on this. And she's been looking at stellar compositions for systems that have this warm dust and trying to get the magnesium and the silicon composition of those host stars such that we can make this comparison. So what I'm showing here is kind of a preliminary plot from her work, which shows kind of a range of systems now where we have the stellar magnesium to silicon, and we have the magnesium to silicon that we deduced from that debris disk dust from the minerals that we see there in the peaky features. There are large error bars in what we're doing, but broadly, we're seeing this kind of one-to-one trend, which is shown by the kind of dashed line across here, that the host stars are matching the minerals that we see in these kind of debris disk systems. So I'm very excited about this work, and Claire's poster is just there, so I'd really encourage you to go and chat to her. I've kind of shown you 2 bits of evidence that we've been thinking about in our group about how exoplanet composition might match host stars. So if we believe this now, well, what can we learn about exoplanets based on this match? So I'm now going to talk about some work by Xander Byrne, who's also sat over here and would love to talk to you about it. And he's been thinking about planets around nearby systems, and in particular Barnard's star. So I got quite excited about Barnard's star. It's only 1.8 parsec away. And so you would think we would know everything about it. It's right on our doorstep. And yet actually it's amazingly hard to kind of characterize even the planets there. So these planets don't transit. They've been detected in radial velocity using Espresso and Maroon X. And there are 4 of them. And so what we're plotting here is the mass against period. And you can see the 4 planets down here with their minimum masses. And those minimum masses are tiny, right? They're much less than Earth mass. So those planets could potentially be a chain of very low mass rocky planets. What's shown in red is the potential for other planets that haven't been detected as yet in the system. And if you kind of compare that to where the habitable zone is for the system, you can see that there's a very low chance that there's a rocky planet in the habitable zone of this star. But there may well be planets further out that we still haven't found. Oh yeah, and this star is a low mass star, so it's an M dwarf. But what's nice is because it's so close by, we can get really, really nice spectra. And so using Spirou, Jahandar et al. In 2024 analyzed the composition of this star. And this is what they found. So I'm just plotting on the y-axis the ratio of each of these elements relative to hydrogen. And you can see that this star is very metal poor. Solar composition is right up the top there. And we can see precise ratios that we can determine of all the different elements that we find there. So what can we learn? Well, if we go back to magnesium to silicon, those are the dominant elements that form kind of the rocks in the planetary mantle. We can use the magnesium to silicon ratio from this star to determine what we think that planetary mantle should be made from. So this star is very magnesium rich relative to the silicon. And so plotted up here on the right is a kind of plot which shows the different minerals as a function of pressure with the kind of planetary surface being on the left here, going right down deep into the interior as you kind of move this way. And what you're seeing from the different colours is the range of different minerals that are predicted to exist inside of the mantle for this planet. And this is based on work from Claire Guimond, who's showing that actually for this kind of magnesium-rich mantle, you get a water storage capacity that's quite high. It's about 1.5 times Earth, 1.5 Earth oceans. And so that's what's plotted at the top here. So you can see how much water that planetary mantle could store. And so this is really fascinating because it means for a planet that is around a very nearby star, even though we only know its mass, we don't even know what the radius is for this planet, we can use the composition of the star to infer what we think the mantle should be like, and even to make constraints on the kind of potential habitability and the ability of that planet's mantle to store water. So we can also learn about other important kind of processes in the interior of planets that exist around this star. So radiogenic heating is really important for kind of fueling the thermal evolution of planets. And in particular, long-lived radiogenic heating is important for Earth, for kind of maintaining some of the heat source in Earth's deep mantle today. And what's nice is that for Barnard's star, we have a measurement for thorium. So we know what the budget of long-lived radioactive nuclides is for this star. And actually, the star is depleted in thorium relative to magnesium. And so what Xander's done is he's used some kind of galactic chemical evolution models to predict from the kind of thorium and magnesium also what we think the uranium and 40 potassium heat budget should be for this planet. And what he finds is that the radiogenic heating in Barnard's star mantle should be less than half that of what it's in Earth today. So the star is depleted in thorium, and so we think there's going to be less heat inside of the mantle of these planets. Now this is super interesting, and we've kind of been in the process of discussing what we think this means in terms of the planet's kind of future trajectory. Radiogenic heating can be really important for convection in that planet's mantle and potentially even for magnetic field generation. So I'm really excited about this kind of potential that we can use host star compositions to really learn about what's going on inside of planets. Yeah, Xander's here, so I'd encourage you to talk to him more about this later today. So we kind of thought about what we can learn about interior, but surfaces are also super important for habitability. If we go back to this kind of picture for Earth, in terms of our own existence, we're very aware that the kind of beautiful continents we have on our planet with kind of mountains and oceans has kind of led to the planet that it's habitable for us today and the very nice place that we were happy to live. But in terms of kind of origins and where we came from, maybe we need to be thinking about something more like this. So if we go back in kind of solar system history to the end of planet formation, where we've already kind of formed Earth, Earth is still molten, we've got a big magma ocean going on. We've grown most of our mass, we formed our core, core formation has kind of finished, but there's still lots and lots of kind of debris left around from those kind of late stages of planet formation. And so that debris can kind of take the form of things that helped and were really good for growing Earth. But now we have a planet that's fully formed. Is that debris going to be good for life, or is it going to be bad and destructive? And so in the kind of next 10 minutes, I'm going to talk about that question of how does that late accretion influence the habitability of planets? And so we can think of it from a variety of perspectives, right? Once you have a planet that's kind of habitable, if we have a dramatic impact like this, who knows what happens to life, right? Those impacts have the potential to be very, very destructive. On the other hand, we need to have volatiles, we need phosphorus, we need sulfur, we need all of these things for life and for habitability. And potentially those could have been delivered by those late impacts onto the surface, onto the place where we most need them for those kind of chemistry, and even kind of feedstock molecules for prebiotic chemistry. If you can deliver those to the surface, maybe that's the best way to kind of kickstart things and help things to move along quickly. So Rich is going to be talking later about exactly how much late accretion Earth had. So we can look at the moon, and we can see a load of craters on the moon. And so we have a minimum idea of what must be going on. We can also look at rocks within the mantle, and we can look at these kind of highly siderophile elements that should have been in Earth's core, but actually are not, and they're in Earth's mantle to kind of tell us about how much material we think should have arrived onto Earth post-formation. And clearly this is going to be really important, because how much late accretion we have is going to determine whether or not this is going to have a positive or a negative effect, or even any effect at all on our planet. And Rich is going to talk a little bit about whether or not Earth really received that kind of 1% of an Earth mass in late delivery that those highly siderophile elements in Earth's mantle might suggest. So I'll leave that to later. But I'm going to talk here about some of the work that we've been doing, thinking about whether or not we can deliver some of those prebiotic feedstock molecules to early Earth that might kind of help us with that origins chemistry. And in particular, this is kind of motivated by the fact that if we look at comets in our solar system, we see lots and lots of organics. We see lots and lots of those feedstock molecules that we would like to have for prebiotic chemistry. And so they become a very tempting reservoir to look at, to say, well, if we took some of that stuff from those comets and we just pop it in a little pond on the surface of the planet, can we then kickstart our kind of prebiotic chemistry and lead to kind of origins? So this is a kind of figure just showing us some of the things that have been detected in comets. And in particular, I kind of want you to focus on here on HCN and cyanoacetylene, that both have been detected in lots and lots of comets. And that's because that kind of CN bond that stores all of the energy that we want to kind of harvest for this prebiotic chemistry, we can create that in the interstellar medium and on those interstellar ice chemistry much more easily than we can kind of on Earth. And so comets that incorporate material from the ISM as pristine interstellar ices contain lots of these material. But there's a big question that's got to happen first, right? So if we want comets to deliver any of this to Earth, we've got to get it onto the surface of Earth. And the problem is that those impacts are going to be violent. So I'm sure some of you remember last year a talk by Katrina MacDonald, who's sadly not with us anymore in Cambridge, but who did some brilliant work. No. Thank you. Who did some really, really interesting, she is happily working for the government. She did some brilliant work on looking at what happens during a cometary impact onto early Earth. And so this is a kind of video of a kilometre-sized body having a grazing impact onto the surface of Earth. And what you can see is that even for this grazing impact, it's pretty crazy. So, I'll try to show it again. So that kind of comes along, and you can see kind of how the body is destroyed. It's pulled apart. Temperatures are reaching kind of thousands of Kelvin in the middle of that comet. And you're spreading material over a large area, several kind of tens of kilometers compared to the size of that thing, which was only a kilometer to start with. So impacts can do a lot of exciting things. So can any of these organics survive in those impacts? So what Katrina did was she traced what the peak temperature was that was experienced by different parts of the comets during those impactors. So this is a relatively low velocity impact at 10 kilometers a second. And what you can see on the left-hand side is kind of where the comet true material, okay, it ends up all spread out in crazy places, but you can see what temperatures it reached. So kind of starting on the left here, you can see really, really high temperatures of kind of 7,000 Kelvin or so right down at the surface. Whereas this top bit at the kind of outer edge of that comet, the bit that kind of didn't experience so much shock heating there, actually stays relatively cool. Yeah, everything's still vaporized, but it's relatively cool. And then what she did is she looked at some of the reactions that would happen at that temperature, bearing in mind that this happens for a very, very short amount of time. So those peak temperatures exist for tiny, tiny amounts of time. And so she looked at how much, for example, HCN could survive inside of these comets. And unsurprisingly, what she found was that actually very, very little HCN can survive. So you can see most of it is at kind of 0% down here. The only place where you can get HCN survival for these comets is right at that kind of tip that edge there, the bit that didn't reach high temperatures for very long on the outer edge of the comet. And what she also found was that you could get these organics or HCN to survive, but only if you have these very grazing impacts. So the head-on impacts are all too fast, but the very, very grazing ones can get a very minimal amount of HCN survival. So then you have to ask the question, well, how often do we have grazing impactors, and what's the velocity distribution of comets hitting the surface of Earth? So comets have to come from Earth, from the outer regions of the solar system, right, from the Kuiper belt, and places where we can form these things. So by the time they've got into Earth, they are on these highly eccentric orbits. And that means that they do, in general, have these relatively high velocities. So what Richard and Kat together have been plotting here is the kind of velocity distribution of comets hitting early Earth based on some kind of numerical simulations. And then the kind of second peak is what happens to that velocity distribution due to atmospheric effects, which can change the distribution from the top of the atmosphere down to the surface, and actually remove some of those kind of low velocity impacts. And so what they found was that most comets that kind of make it to the surface actually have very high velocities. So what does it mean for the ability of comets to deliver these kind of prebiotic feedstock molecules for Earth? Well, if we start with this kind of model, we can say we have a distribution of comets in the outer solar system. We know what their velocity distribution is when they reach Earth. We know what the distribution of angles when they reach Earth. And we know how much HCN survives depending on all of those properties. And we can use that to predict how many comets deliver some HCN that might be useful for prebiotic chemistry. So we start with the kind of right axis of this plot. What Rich is plotting here is the number of comets that deliver more than 10 millimolar of HCN per megayear as a function of kind of time in solar system history. So what you can see is that if we want to get cometary delivery, we need to go very, very early in solar system history to kind of times when we actually had lots of impacts and that impact flux was much, much higher. So if we kind of put ourselves before about 4.5 gigayears, then there's a 1 in 100 chance of us getting a comet that delivers enough HCN per megayear to kind of make this work. Another way of saying it is if we kind of have many realizations of solar system history that we can put on the left side here, then we can say the fraction of those simulations where we have a successful impactor that delivers some HCN that happened at a time later than t. And you can see the kind of red curve, and you can see that basically we're really limited to kind of very, very early times in solar system history, potentially even before we had kind of enough surface for this prebiotic delivery to be useful for us. So what we're kind of concluding from this is that we don't think that cometary delivery of prebiotic feedstock molecules is a very unlikely scenario for early Earth. There's still a chance it happened, but that chance is very small, and it has to be limited to very, very early in Earth's history. So hopefully I've given you a kind of whistle-top tour of things that we've been thinking about in our group related to kind of composition and habitability. I'm very excited about the next 10 years of rocky exoplanet detection. There's a lot of really, really good stuff coming on. And we're going to have lots more planetary candidates to kind of think about, but it's still going to be hard to constrain their interiors. And so hopefully I've persuaded you that host stars and the composition of host stars are a brilliant way of learning about the interiors of those rocky exoplanets, and that we have some good evidence actually about that match between host star and planetary composition, particularly for refractory elements from these kind of wide binary systems and warm debris disks. Host stars can tell us about mantle mineralogy, can tell us about how much heating you have and the thermal evolution of the planets. And so I think going forwards, we need to make use of all of the information that we have to learn about any potential rocky planet candidates that we have for their habitability. And then the second half of the talk, I talked about late accretion and whether or not late accretion is good for origin scenarios for planets. And actually, the fact that cometary delivery of prebiotic feedstock molecules to early Earth is really tough and is really an unlikely kind of source of the HCN that we might need for origin scenario on Earth. I'm happy to take any questions. Thank you for listening.